Good morning. Welcome on behalf of the Western States Seismic Policy Council to this seminar on earthquake early warning. My name is Jim Golds. I'm the Earthquake and Tsunami Program Manager for the California Emergency Management Agency. I'll serve as moderator for today's session. I would like to mention that the session is going to be videotaped. That will be available, the presentations will be available to you hopefully next month on the WSSPC website. At the beginning of my career, many years ago, we had some optimism that we might have reliable scientific earthquake predictions in the near future. That is, a statement of the time, location, magnitude, and probability of occurrence of an earthquake that would occur in the hours, days, weeks, months ahead of time. Unfortunately, that hope was not realized, at least up to this point. But I think that we have made very significant gains in providing accurate real-time seismic information immediately during and following the initiation of an earthquake. We have very rapidly available source information, magnitude, location, time of occurrence, depth, in a matter of seconds. We have mapped ground motion through Shake Map and the Community Internet Intensity Map in the first few minutes after the occurrence of an earthquake. We have aftershock probabilities, and we have something called the Prompt Assessment of Global Earthquakes for Response, which combines the availability of source information with mapping and also the exposure of population to various levels of ground motion. So, earthquake early warning offers a possibility of expanding real-time information about the possible existence and effects of an evolving seismic sequence. Now, our hope is that if we have a few seconds to a few tens of seconds advanced warning of approaching ground motion, we may be able to save lives and also reduce property damage. Today, we have 4 very qualified speakers talk about earthquake early warning with an emphasis on applications. We have David Applegate, who is Senior Science Advisor for Earthquake and Geologic Hazards for the U.S. Geological Survey in Reston, Virginia. We have Dennis Milletti, who is Professor Emeritus of Sociology and a former Director of the Natural Hazards Center at the University of Colorado Boulder. David Zacchetti is Chief Counsel and Director of Legislative Affairs for the California Emergency Management Agency. And Yukio Fujinawa is Senior Managing Director of the Real-Time Information Consortium based in Tokyo, Japan. Our panel presentations today will bring you up to date on research being conducted in the U.S. on earthquake early warning, address some of the societal challenges and opportunities that earthquake early warning may present. We'll address the legal and institutional implications for the implementation of an earthquake early warning system in the U.S. and provide some insights on earthquake early warning from the system that's been in place in Japan since October of 2007. Our first speaker is Dr. David Applegate. He is Senior Advisor for Earthquake and Geologic Hazards with the U.S. Geological Survey and leads the Earthquake Hazards Global Seismic Network and Geomagnetism programs for the USGS. He also chairs the National Science and Technology Council's Interagency Subcommittee on Disaster Reduction. David.
All right. Thank you, Jim, and I'd encourage if the rest of the panel wants to be out in the audience instead of in front of these Klieg lights, you're welcome to do that. Great, we switched to this computer. Well, appreciate the opportunity to be here, and what I'd like to actually start with to sort of frame this, to frame both the challenges and the opportunities, is I'd like to show you two different scenarios for what would be catastrophic earthquakes in California, and use those as something of a backdrop here for talking about what we mean with early warning. Now, this first one is the scenarios used for the Great Southern California Shakeout. It's for magnitude 7.8 in Southern California, and let's look at what we're looking at here. The earthquake has begun, and this is a key point for early warning. It's not about earthquake prediction. An earthquake has already begun down at the Salton Sea, and it's making its way up to the north. And now here we are looking, we're in downtown LA looking south. So here's the opportunity of early warning. The shaking has not yet arrived in downtown LA. We're already at 30 seconds. We haven't even received the P wave. On the other hand, the folks down at the epicenter, even when under the best circumstances where we have instrumentation right there, we can get the information out right away, they're going to be in a blind zone. Okay, so we just got the first bump, and some early warning systems are based very much on a local, the experience of the first bump, the P wave, and then being able to issue a local warning before the arrival of the strong shaking. But from a network standpoint, what you're trying to do is actually get the information out from the epicentral area to everyone who is potentially going to be affected. So here we are, we're now at 71 seconds, and the first of the strong surface waves are arriving in downtown Los Angeles. So this gives you from a sort of, almost, I put it a best case scenario, although having a 7.8 earthquake hitting Southern California is not anybody's idea of a best case scenario. But it certainly underscores this is the opportunity for early warning to be getting information out before strong shaking arrives. And so you can be thinking about it as you're sitting there listening about what is it that you'd be able to do in that kind of a time frame. But now I want to show you a second animation, and this is for the other, what we consider the other most likely catastrophic earthquake that would strike California, and this is the Hayward Fault in the Bay Area. So here's the Bay Area. It's going to nucleate down here at the southern end of the bay and propagate up. And of course, the Hayward Fault is right now. It's been 142 years, I guess, since the last one. It's got an average recurrence interval of 140 years. So it's certainly due, and it is. People talk about the San Andreas 1906 being the big one, and the Hayward being the bad one, because as you see, it goes right through the urban area. So that's the. So let's see how this plays out. All right. So this is the case. The earthquake is starting down in the south. The earthquake has occurred, and almost immediately we have the P wave coming through the dense urban area in Oakland, also reaching across to the Bay Area, and the strong shaking following very rapidly thereafter. So I just want to underscore the way we look at early warning is that any system that gets developed, it has to be an outgrowth of what we're already doing, which is trying to provide the fastest possible information in the most rich and robust information following an earthquake, because in any given earthquake, in varying degrees, there will be those who could get a warning before shaking starts, and we're very fortunate to have a presentation from Japan where they have this operational system. But in any earthquake, there will be an awful lot of folks who are not going to be getting that warning. And so that's one of the challenges for expectations. Okay, so returning to slides here. So this is the example that I just showed you from the shakeout scenario. As I said, there's going to be this blind zone, even if you can get the data out immediately from a robust network of stations and get it to a processing center and get the information disseminated. You can get more time in, say, San Bernardino, and you can get a considerable amount of time in downtown LA. So that's the potential. But to do this, you need to have those stations. You need robust seismic networks, you need robust communications, you need robust processing, you need robust notification capability, and you need significant user education and participation. And this system, as developed, will only be as good as the thought that's put into how it is going to be put to use. And I think you'll hear from following speakers on the sort of user perspective, but just throwing out, what are some of the ways that people have envisioned a warning system being used? What are some of the ways that it is being used? The stopping elevators in a high-rise type situation, factories being able to stop delicate processes. We already have some good examples from Japan of the ability to put equipment into a safe mode before strong shaking arrives, and with some significant costs averted from that. Trains, slowing down the trains. Of course, the slower the train is going, the less likely for derailment. Nuclear facilities, putting it into a safe mode, putting control rods in. Airports, from a standpoint of, well, I think it's pretty obvious, planes arriving and landings. Bridges, being able to keep bring the gates down to prevent there being large numbers out on a vulnerable bridge. Utilities, of course, utilities is a very interesting question about how that would be used from an early warning standpoint. Would utilities use that time to actually shut down systems? There's some fascinating liability issues, and we'll be hearing from our third speaker about some of the sort of legal ramifications of early warning. But just the situational awareness of having more time to be able to do load balancing, whatever it might be. Freeways, using something like the existing Amber Alert system to be able to issue notifications there. Schools, the goal of getting kids under the desks. I saw Kay Long's got her drop cover and hold on t-shirt there from the shakeout, and that would be another one. And construction sites, heavy equipment, again, the idea that you can have time to get into a safe mode. So those are some of the ideas that are out there and the ways that you could use an early warning system. Now, we are fortunate in that we're not leading the pack here. Indeed, there are a number of countries that have already implemented early warning systems. In blue here, the active systems: Mexico, for Mexico City, Bucharest, Romania, Istanbul, Turkey, Taipei, Taiwan, and of course the system we're going to be hearing about more in Japan, which really is the gold standard. And of those systems, two of them, Mexico and Japan, are issuing public announcements associated with this, as opposed to notifications, say, to emergency management. And that's this slide, I should say, from Richard Allen at UC Berkeley, and Richard's been leading the charge in what I'll be talking about with algorithm development and prototype testing, and a partnership that the USGS has supported.